Vibration, a fundamental phenomenon in physics, is characterized by the oscillatory motion of objects. To understand this complex behavior, we can deconstruct vibration into its core components: amplitude, frequency, phase, damping, and energy. By examining the relationships between these components using logical patterns, we can gain deeper insights into how they interact and influence each other. Here, we focus on the most instructive triads of these components and explore their interactions within different logical frameworks. In the context of vibration, the coexistence of amplitude, A, frequency, F, and phase, P, represents a state of perfect synchronization. When a system is in resonance, changes in amplitude directly affect frequency and phase. For example, a guitar string vibrates at a certain frequency, producing a specific sound. The amplitude of the string's displacement determines the loudness, while the phase indicates the position of the string at any given time. This triad can be seen in many natural and engineered systems where resonance occurs. A tuning fork, when struck, exhibits a stable relationship between its amplitude, frequency, and phase, resulting in a pure tone. Understanding this coexistence helps engineers design systems that avoid destructive resonance, such as in buildings and bridges, by ensuring components vibrate harmoniously. Reinforcement in vibrating systems describes how changes in one component can amplify others. When amplitude increases, the energy stored in the system also increases, which in turn can affect the frequency of vibration. This reinforcing loop can lead to significant energy buildup, as seen in phenomena like earthquakes or the Tacoma Narrows Bridge collapse, where oscillations grew uncontrollably. For example, consider a child's swing. As the child pumps their legs, increasing amplitude, the swing moves higher, storing more energy, which affects the frequency of the swings. This reinforcing mechanism can be harnessed in applications like energy harvesting, where vibrational energy is converted into electrical power. Causal relationships in vibration indicate a direct influence from one component to another. A change in amplitude causes a change in frequency, which in turn affects the phase. If there is no amplitude, A, the phase is also 0, or P, indicating no oscillation. This is fundamental in systems where precise control of vibration is necessary, such as in electronic signal processing or musical instrument tuning. For instance, in an electronic oscillator, adjusting the amplitude of the signal can change the frequency and phase of the output. This principle is critical in designing circuits that require stable and predictable oscillatory behavior, such as clocks in computers and communication systems. Harmonic interactions represent conditions where combinations of amplitude and frequency determine the phase, and similarly for other pairs. This triad is essential in understanding harmonic oscillations and resonance phenomena, where the interplay between these components creates stable and predictable patterns. A classic example is the harmonic motion of a pendulum, where the amplitude of the swing and the frequency determine the phase of the motion. Harmonic relationships are also crucial in musical instruments, where the combination of string tension, amplitude, and length, frequency, determines the pitch and tone quality, phase, of the sound produced. Nonlinear interactions describe systems where small changes in one component can cause large changes in another, often leading to complex and unpredictable behavior. In vibrational systems, amplitude affects energy in a nonlinear way, and energy influences frequency. This can result in phenomena such as harmonics, where the system oscillates at multiple frequencies simultaneously. For example, in a vibrating membrane like a drumhead, small increases in amplitude can lead to significant energy changes, affecting the vibrational modes and frequencies produced. Understanding these nonlinear relationships helps in designing instruments and structures that can withstand or utilize complex vibrational patterns. By examining the components of vibration through these logical patterns, we gain a structured understanding of their interactions and dependencies. This approach provides valuable insights into designing systems that control or exploit vibration effectively. Whether in engineering, musical instrument design, or natural phenomena, understanding these relationships is crucial for predicting and managing vibrational behavior.